Okay. Okay, so welcome everyone. We're super excited today for the last Talkboctopus of the seminar series for the spring. So today we have Demival, Vasques Filho joining us, and so Demival has an interesting background with a bachelor's in physics engineering, and unlike a lot of us, he actually spent time in the real world, working in industry for many years. So that gave him a very interesting perspective when he joined back for a PhD at the University of Auckland in New Zealand, working with a friend of the center, Diane O'Neill, on bipartite network and their use in technology, politics, the science of science, and kind of revolutionize the bipartite network analysis field. And so these days, Demival is working at the Leibniz Institute for European History in Mainz in Germany, kind of doing digital humanities. And today he'll be talking to us about how to use these network analysis at the population scale. We're super happy to have you here, and the floor is yours.
Thank you very much. I'm super happy to be here, and thank you for inviting me. Okay, so yeah, let's talk about this thing, building a framework for population scale network analysis. I put the emphasis on building because yeah, it's still something that we are thinking about a lot. How to improve our measures and methods, how to look better at data to create a population scale network analysis. And when we talk about population scale network analysis, it comes to mind, of course, epidemics, and you've been seeing this during the pandemic, but also things like social processes like cohesion, inequality, segregation, and so on. Right? So that's the sense that we are looking here. Right. So for the talk today, the outline is first, I'm just going to talk about the structure of higher order interactions and what we think is important to look at those networks that have those kind of interactions. Then I'll quickly talk about how we build a population network in New Zealand when the pandemic came, and then we start working on assisting government with its response to the pandemic there in New Zealand. And then then I'm gonna go into the framework, like what we're thinking that it's important to look at when we are talking about network analysis for like an entire society, things like this. So let's go starting like with high order interaction. So how do we see high order interactions? I think like this is just like a nice name to represent or to define collective interactions, right? So when we are groups of people, so if we are like a dinner table with friends, and then we are more than two people talking with each other, so we have a group interaction, there are collective interaction, and then we decided to call these things as higher order interactions because it goes above 2, 3, 4 people interacting at the same time, right? And how do we represent them? So mostly you have three ways of representing this. Like one is using bipartite networks and projections. So we have, for example, here 3 students in the classroom or doing a task for the classroom, and then they are connected to each other because they're in a group doing some project together. But then we can do that too as a hypergraph, and then here we just represent this 2 hyper edge. So we have this hyper edge or hyperlink that connecting the 3 of them. And instead of having those 2 entities, not 2 entities, yeah, 2 entities like the individuals and the group itself, like the project that we're working on or the dinner table that I just mentioned. Now we have like we are focused on the individuals, and the groupment it's based on the hyper edge, and we have simplicial complex as well that we can do that, right? The focus here, as we're going to see, is going to be bipartite networking projections because the concepts we can go from bipartite networks to hypergraphs to simplicial complexes, we of course, mathematically, they differ from each other, but the main idea that I want to talk here about the concepts. And the concepts we can go across independently of how we represent these higher order interactions. Yeah. So when we think about traditional pairwise network structure, I think the main features that when we look at it is the degree. And then here I'm already putting this in parentheses, like the neighborhood size, so I can do some kind of a parallel. So we are concerned about the degree distribution, and we are concerned about the triangles that that the network has, right? So be it transitivity or local clustering with the average local clustering. But when we look at higher order interactions, then we have to think of other things, right? So I'm calling the degree distribution in a sense of the number of edges adjacent to the node as activity. So activity here means to how many collective interactions an individual is part of, right? So that's, and I'm going to use this term activity instead of degree, so we can separate things and don't make a confusion about it. Right? The other thing that I have to look at is the circle size distribution or group size distribution, but I'm going to use circle here again to differentiate group from like religious groups or ethnic groups and so on. So I use the term circle to represent these collectivities. And the other features that I think is extremely important for higher order interactions are the overlaps in the 6 cycles. And 6 cycles is a specific thing of bipartite networks, as we will see, right? And why these features are so important? Because actually, what we are looking at is that they result in popularity, which is the neighborhood size distribution. So now we can see that popularity here, I'm calling popularity what we call degree distributions in traditional networks. Then we're going to have strength distribution, and we are going to look at a triangle. So the thing is that these features of higher order networks result in that, like in triangles now. So triangles is not like the main feature driving, but now it's a consequence of it. And the popularity or the neighborhood size distribution, the same thing. So as I go along the talk, you're going to see that these main features of higher order networks are actually what the mechanisms that we are arguing that create the social structure in terms of patterns of relationships, right? So we start this looking first at these distributions. So there's these papers that we did study focus on degree distribution of bipartite networks and their projections. And the main thing that we wanted to put as like more pedagogical way is to like really think about what bipartite networks are and what kind of projections we can do, right? Because in the literature, it was still a bit confusing what kind of projections we could use, what a degree in a simple graph means, what a degree in a multigraph means, and so on. So we started putting this as like, okay, in a pedagogical way, simple graph, multigraph, and weighted graph networks as projection of bipartite networks. And what does it mean, right? So in a simple graph, the popularity is just the same number of the number of interactions that a node has, right? While in a multigraph, the popularity is different than interactions. Like the interactions are actually the strength of the node. So for example, A and B here in the multigraph, they both have a strength of 3, but popularity of 2, right? So we have to make this differentiation already when we are creating projections. And when we come to weighted graph, a weighted graph kind of brings the two together. So popularity is the number of interactions in terms of unique interactions with other people, while the weight is the strength. And then when we sum the weight of all the edges adjacent to a node, then we have the strength. Okay. So in a sense, the popularity of a node, so the popularity of a node U is given by the sum of all the activity of this node and the size of this activity in terms of the circle, like so the size of the circle that the node is part of minus the node itself, that's why the -1, and that gives popularity. But we have this thing, this inequality here, right? And when we start looking at the structure of the degree distributions of bipartite networks and projections, we are wondering, what does this inequality mean, right? And what does the strength have to do with this? So the strength is when the equality holds, right? So when this equation just have an equality, and that's what this equation had been in the literature before, but always with the equality. And we are arguing that equality in this equation means just the strength of a node, but not the popularity. And we're going to see how we came to these conclusions. So what we did in this paper is that we use configuration models with a combination of distributions for both activity and circle size, and we use probability distributions for the configurations model from peak to head tail distribution. So we use delta functions, as like every node has the same activity, or every circle has the same size, and so in Poisson distribution, exponential distribution, and so on. So here, for example, we have a graph that what's the popularity / strength distribution. So the simple graph is the popularity distribution, and the multigraph is the strength distribution. When we have as the circle size distribution the Poisson, exponential, and power law distribution, and the activity distribution is it's power law like, right? And if you take, like, for example, just the Poisson, compare with the popularity with the strength, so the blue and the red here, we see that there's this gap between the two distributions. So this one's the strength distribution. It's kind of the upper bound of what we expect when we have certain activity and circle size distributions. And in the paper, we analytically solve some of these cases with generating functions. But I think the key thing here is that we can predict, according to the circle size distribution and activity distribution, we can predict the strength distribution. But popularity, we have that question mark. We don't know. So the key takeaways from this paper is that the popularity distribution tends to follow the shape of the activity distribution. That was pretty nice. So most of the time, this popularity distribution will actually follow the activity of a distribution. But if the circle size distribution has a heavier tail, then this pattern breaks, right? And that's why we are trying to understand too how these distributions affect the popularity distribution. And like I said before, the strength distribution then is upper bound for popularity. And then, okay, now we know that there's this gap between strength distribution, popularity distribution of the nodes, but what's more about this? What's more about the structure of bipartite networks and projections? So when we start analyzing collaboration networks of patents, we start seeing what was going on there to explain that. And what we found is that we saw many of these motifs in the patent collaboration network, right? So we had what we call in the paper force cycle, which is the same thing I'm calling here as overlap, and SIG cycle. And the force cycle is what creates redundancy, and then that's what starts to make the gap between strength distribution and popularity distribution wider. And SIG cycle is when we have situations like like for example, A and C is part of a separate group, A and B in in yet another group, and B and C in another group. And that sixth cycle in the higher order interaction network is what creates triadic closure, right? So that's what we start to see. And when we talk, okay, how much does these motives actually interfere in the structure, or how relevant they are, right? And then we start counting these cycles, and we see that the empirical network has way more things, 4 cycles, 6 cycle, 8 cycle, and so on. This what we call small cycles, than the configuration model. And if you look especially at the 4 cycles, we start thinking how is these 4 cycles actually affecting the behavior? In our case, we're studying like institutions developing patents, how this can affect the behavior of these institutions. And then we come with this very simple ratio that we call diversity, which is just the popularity over the strength of a node, right? So here's the degree of the activity, the degree of a node in a simple graph is in the multi-graph, and we call popularity and strength, right? So with only this simple ratio of popularity strength of institution in this case, we could see different strategies for collaboration when creating patents, for example, right? And then this became something that we started thinking more when we start talking about population, like entire populations too. And the other thing that we did is that we start thinking about, okay, now that we understand a bit better these things of bipartite networking projections, or like the structure of higher order networks, is there anything to do with this thing that social networks are different than non-social networks in terms of transitivity and degree assortativity? So this has been for long a discussion, and there was this question like, is higher transitivity and degree assortativity in social networks due to bipartite data, or due to modeling based on groups or circles? And what is about this artificial clustering when we have like these huge groups, and then we think about their connections, they create cliques, right? So if you have a group of 5 people, then everybody's connected to each other. So we have this clique, and this clique has a lot of triangles. And then is this possible that is this this case is that's creating the higher transitivity of social networks? So in this paper, we tackled this problem in particular. So let's just think about transitivity as the number of closed triplets over the number of triplets, and then you know that's 3 times the number of triangles over the total number of triplets in the network. And what we say is that clustering social higher order networks emerge from a balance between the circle size distribution, activity distribution, and favored by overlaps in 6 cycles. So let's put this step by step. So circle size and activity distribution, for example. First, circle size. That's what's been saying as artificial clustering. Large circles increase clustering because we know that one group creates triangles as n choose 3, n being the size of the group. And then as the group grows, the number of triangles goes at n to the third, proportional to n to the third. So it goes really fast. So if we have big groups, or big circles, I'm sorry, let me stick to the term. So if we have big circles, then we know that we have this huge number of triangles. But that's not only the case, right? So if you have high activity, and high degree here it's meant activity, that happens to increase the number of upper triplets, because let's say that we have a node that's the intersection between two circles. So the number of open triplets that exist because of this node takes this kind of equation. So it's kind of like the size of one circle times the size of the other circle. So it creates a lot of open triplets. So if I have a heavy tail distribution for the activity of people, then our transitivity is going to decrease, right? So it's a balance. So with that, we kind of answer that question. It's like, is this because of modeling with bipartite data and group-based or circle-based? Not really. It's just because the way of the data that we have available, like collaboration at work in papers, right? That we have like physicists collaborating with hundreds of people, and that kind of create a bias, and then we start thinking, oh, okay, because social networks have higher large groups, then we have higher clustering or higher transitivity. It depends. It really depends on the two distributions. And also depends on the overlapping and 6 cycles, because like I said, 6 cycles is the representative of triadic closure in high order networks. Right? So the more we have, then the more triangles we have. And overlapping decreases the number of open triplets. So the more overlaps we have, the more happens that it's not only one node intersecting two circles, it's more than one node, and then the number of open triplets decrease as well. So in a sense, as a summary, we have that large circles favor increasing transitivity. However, high activity favor reducing transitivity, and overlaps in 6 cycles increase transitivity as well. So we have to think of all these things to talk about clustering in the network, right? And the same in the same conclusions is for degree assortativity as well, but I'm going to leave that apart for now. But the same conclusions is valid for degree assortativity too. Right? Okay, so now we enter how we got everything together to create this population scale network in New Zealand, using these concepts that we've been working before, right? So when the pandemic started and the group started working on how to model this using network-based approach, we had access to that data like census, and so we have, okay, age, sex, ethnicity of like the whole population in New Zealand, and we're talking about 5 million people here. Data on educations in the educational system and employment and mobility. But of course, we had the issue of anonymization too. So we had to deal with this data to a certain level of anonymization. Then we had to start creating models. And when the models we decided to create was entirely based on the bipartite networks, right? So this has been done before in study of epidemics, like several layers layers of interactions between people. But the thing here is that we decided to model as a bipartite network and not as a projection, that was usually done, right? So the layers that we used was the dwelling, so the information from the census from household, and with the size of the household would be the size of the circles, the size of the workplaces, again, size of different kind of circles, schools, and then finally community. And for this community, this was the most challenging part, apart from the data, dealing with the data, because we didn't have information about the community in the sense of which are the circles in the community. Like people going to church or to the mosque or to sport clubs or book clubs whatsoever. It doesn't matter. But what kind of circles those communities can have, right? And that part was the of when we created these networks was the part that we dealt most with, let's say, educated guests, because we didn't have the data for those circles. So we had data for the dwelling on households with the distribution of the size of these households, the distribution of this, the size of the workplaces, the size of the schools, but the communities we didn't have. So that was challenging. And then we use all together to build this bipartite network, which the layers that we are putting here actually were the attributes of the circles. So we had circles that were workplaces, circles that schools, and so we kind of created a concept of a multi-layer bipartite network to develop the models here. And after and during that, of course, we were learning the process, and there was this demand for rapid information from the government, and it was interesting that as we were developing the model, we came with open questions and we reported at the same time, such that the papers were not published, because I think it was like a learning process, and it was just like published as reports. But the open questions that we had, the most important, I would say, first is like the distinction between circles and the events happening within the circle. So for example, okay, we have a workplace that's a circle, but we know that in a workplace we have like meetings, we have gatherings, we have collaborations, and so on, and these we call events. So how do we deal with that? We don't have data for that, like in a society or in the level of the whole population, right? So that was one of the big challenges and the open questions that, okay, we have now to target how we can see how events happen, like when people go to church or to the mosque. How does it work, these events that are part of the circles? And I hope when I talk about the framework, that will be a bit clearer. The other thing is circle size. At which level should we look when we're talking about circle size? What's a circle? It's a company, a circle, a company with thousands or tens of thousands of words. Can we call it a circle? Or we should look at the unit, department, a team. So because in a sense this is extremely important, as we saw, the circle size distribution has a huge effect on the neighborhood size. So how many people we interact, right? And then we start asking these questions: what's a circle? And the community circles, as I mentioned, like how do we get meaningful data on them? Like what kind of information do we need to fill this gap of like just having an educated guess of what community circles are? And then from that, we start building this framework from population scale network analysis. And apart from New Zealand, I know that in the Netherlands, they have this initiative called PopNet, that they are doing a similar thing, trying to develop infrastructure to analyze a whole population of the Netherlands. So it's about 70 million people. Right? So we've talked already a little bit. I shared the experience of the New Zealand case with them too. So it's a really interesting initiative to keep an eye on for everybody that's interested in this kind of research. So okay, so let's see how we start building this, and then I just uploaded a preprint that I called "Mechanisms and Emergent Properties of Social Structure: The Duality of Actors in Social Circles." This is a very first draft of the ideas behind this, so we can model better population scale networks. And the main background for that are some papers. First of them from Scott Feld, the Focus Organization of Social Ties. So in this paper, Feld argues that we all are part of circles, and this is actually coming from sociologist Georg Simmel in the beginning of the 20s, already metaphorically, but not speaking in terms of network analysis, but metaphorically talking about social structure and networks and personal networks, that circles are actually the building blocks of the social structure, right? And Feld used this thing to say, yes, we create connections because we are focused on certain activities, common activities, like we play football or soccer together, we go to dinners together, and so on. So the creation of personal networks, personal relationships, or social ties uh, revolve around circles and the focus that those circles have. Right? The second one was, of course, the fundamental paper that for network analysis in bipartite two-mode networks by Brager, the duality of persons and groups. And I think it's important to point out this paper because the idea of using bipartite or two-mode networks for this particular thing instead of hypergraphs or simplicial complexes is that, as we see, the circles might have attributes and might have agency too. So it's not only the individuals that have attributes and agency, the circles, they can have that too. And then can be important, again, for the structure of the social ties. And thirdly, Robert Hind, with his paper Interactions, Relationships, and Social Structure, when he kind of gives a theory of what social structure is, when we have several interactions, and then from these interactions develop into relationships, and these relationships then map the structure of the network, of the whole society or societies at large. So the idea is that, okay, we can model social structure then as a two-mode or bipartite network, having social circles and actors. When both actors in social circles have attributes and agency, but we always look at the actors only to see how this personal social ties are developing or are structured. Right? And then what if you have this perspective, then we have to think about the mechanisms that are creating these features that we are used to talking about, right? So these features, I mean, like strength heterogeneity, popularity heterogeneity, high cluster, high transitivity, community formation, are result of mainly, not all of it, but mainly homophily, social activity, which is the activity that I'm talking about, and overlaps, right? So homophily, social activity and overlaps, they kind of give the shape of the bipartite network structure. And by consequence, they give the shape of our interpersonal relationships. Right? So that's the main idea here. All right. So then, how one interacts with each other. So then we go back to the beginning when we were talking about the structure of higher order networks. So the idea is that the popularity of a person or the popularity that we see in a society, the distribution of popularity results from the distribution of the activity modulated by distribution of the circle size and the level of overlapping. So here's just like a recapitulation of what I said before, right? But let's see how that works to try to make it more in a clear way. So let's say that Alice and Bob are siblings, live in the same house, a circle house, and going to the same circle school, but they have different interests, right? So like, for example, Bob likes music and he has this circle orchestra with 15 other colleagues, peers, right? And Alice likes to play football or soccer. I'm not sure now. Alice likes to play soccer, let's say, but also she has a reading club and she's interested in learning Portuguese, right? So, so she has like these 3 extra circles, and Bob has 1 extra circle. And then if you look at their interpersonal relationship, uh, Bob has 15 plus, plus because of the house and the school, possible relationships. Alice has 20 plus possible relationships, right? But then it's just if you look specifically at the distribution of activity. If we think of, if you change the distribution of the circle size, so we have the same configuration here, but now Alice, instead of going to a course, for a language course, Alice takes private class lessons, right? So what happened here is, although Alice has more activity than Bob, she has a smaller potential of creating or more larger interpersonal networks, let's say, right? So the circle size is really modulating here the distribution of the activity of Alice, right? And the other thing that can be modulated is the level of overlapping. So let's say, again, we have the original configuration. So Alice plays soccer with her mates, with the 6 other 5 people in the book club, 11 in the college, in the language course. But the thing is, let's say that now everyone in the soccer team is doing the language course too, because they want to spend a season in Brazil practicing soccer, let's say, okay? So now, even though Alice has a higher activity, her circles are larger, she still has a smaller potential in terms of how many people is part of her interpersonal networks, right? So that's how everything that I talked in the beginning actually now comes to represent what we mean about these distributions of activity, distributions of popularity, strength, and so on. Right? So now we get back to that equation, and again we have like popularity is the sum over all the activity of a person, considering the circle size of these activities, and overlap. So overlap is actually the responsible for this inequality in the way that I just showed. How like if a person has a lot of overlaps, then the potential of a larger interpersonal network decreases. So overlap it's, as far as I know, pretty much overlooked, and I think it's actually a really important thing to bear in mind, especially when we're talking about social networks and population scale networks, right? And why is that? I truly think that overlap plays a big role in the formation of communities and how cohesive or how segregated a network can be, right? And for that, I take back like the initial or one of the fundamental works about balance structure. And we look at this paper by Heiter and the attitudes of cognitive organization, there's this part that he says positive or negative relationship of a person P to another person O, or to an impersonal entity X. That's important, the impersonal entity X. So here is when the circle as an impersonal entity gets important in the sense of having attributes or having agency, right? So in a sense, people get together because they have a preference towards some activity, be it playing football, be it playing in a band, or be it working together as engineers in a factory, for example, right? And uh, and how does this reflect the structure of society? So then we have to think that society then has those like heterogeneous circles and homogeneous circles. So we can have a different bunch of types of circles, and that again, that's what's important about agency and attributes of these circles. And if you have, for example, heterogeneous circles, so we might have everybody connected, almost everybody connect to each other here, or we have at least um, uh, uh, connected network, a largest component, let's say, right? But when we have like such homogeneous circles as religious circles can be, or religious schools can be, for example, then we have a clear distinction, and perhaps we have here a fragmentation of the network, uh, or only segregation, but perhaps also a fragmentation of the network, right? And this is completely related to homophily in the sense that people belong to circles according to their interests, and the circles they have these characteristics that will um impact how their interpersonal networks are, and the overlaps happen more when we have these homogeneous circles, and when we have that, we have like more distinct parts of the network. So this is an ongoing work. I'm using configuration models again, uh, with several probability distributions for circle size and activity distribution. But now what I do is that to 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 account these overlaps, when assigning size to circles and activity to individuals, after doing this, then individuals are connected to circles with and it creates overlaps in the probability p, right? Just that. So with a probability p, we have more overlaps in the network. And then what happens is that as this probability increases, then the modularity of the network increases. And I'm not for this. I just use the Louvain method and not judging if like the community detection is the best one or not, leaving that part apart. But the important thing here is that as we have more overlaps, the modularity of the network increases, right? So in a sense, uh, the conclusion that we have is that the more overlaps a network has, the more well-defined the communities in this network, the communities in the network are. Right? So here is kind of like a kind of gave you an idea of this whole uh, relationship between circles and individuals, and size of circles and activity of individuals with all this overlap. But finally, I want to talk about the events that happen within the circle, right? So I think these events are really important because the uh, they are going to be the ones that will tell us the quality, or we can call it bandwidth or weight of the ties in a network, right? So the idea is that when you are part of a circle, you kind of have an opportunity space of knowing all those people belonging to that circle. But then the events that happen within the circle is actually what's gonna say how the relationships will evolve, right? So just to give an idea, so here again we have a two-mode network with a social circle here at school, the kids to the school. So when we do the projection or the interpersonal networks, we see they are all connected together. But this is the opportunity that they have, right? But then the relationship will change as the events that they belong. So if they belong to events together, their relationship can, for example, increase and be better and be more intimate or so on. Of course, here I'm just talking about like positive interactions, and then we can have discussions about negative interactions and so on. But this is something that I think when we're talking about population scale networks, it's something that we have to start debating. how is this event? So if kids go to school, let's not ask them what their best friends are, but which kind of events they participate, right? And based on these events, let's try to then infer what their best friends are, right? These kind of things. So with that, I leave more open questions that we're still thinking about, and that's why we're still like building the framework. So again, the one that I just said, like strong ties or bandwidth within a circle, how we define this, how these patterns emerge, positive interactions, negative interactions, quality of interactions. Exogenous events. So I just talked about events within circles, but we can have exogenous events, like events that happen outside circles. So let's say I belong to a circle, my friend belongs to another circle, and then I go to dinner and I invite one from a circle and this friend from another circle, and then they meet each other, and then that's the kind of a triad closure happening there. And this is not part of any circle. But then if the three of us start going out, hanging out many times, and perhaps we create a band or some sort of circle, when does that informal ties actually become a circle? You know, these kind of questions we're still like having to think about. Again, the circle size, what's the size of the limit? Because you can think of perhaps the Earth, you know, is a circle. So everybody's connected because it's part of Earth. But and of course, I'm going to the extreme here, but that's the kind of thing that we have to think about. Does it make sense to think of a circle as like a company with tens of thousands of employees, or we have to look more inside the structure of this company? And looking at all the circles attributes, like how heterogeneous or homogeneous they are, and how they affect the quality of time. Like, so if I'm in a religious circle and I have events there, the quality of the ties are going to be the same as the workplace, the workplace circle, and when I have events at the workplace. So how different circles affect the quality of the ties too, right? Activity, right? So some people are much more active than others. So we have like some psychological issues, we have resource issues, time issues. So we know that activity it's a heavy tail distribution. So, but where this distribution come from? Which factors or resources play relevant roles in that? Right? The overlaps. Can we have control over them? So, like, can we create policies to create more cohesive societies? So, for example, there was a nice study, I think, in Science that I forgot her name now, but the main thing was that people from different religion were put together to play mixed to play soccer championship, and then in the end they could see that there was more tolerance after this championship. So can we kind of create these things, and then in a sense, what we're doing here is like we do policies to create more heterogeneous circles. We kind of like dealing exactly with overlaps, decreasing the number of overlaps, and then perhaps creating more cohesive societies. And diversity that I talked there in the beginning, the diversity means some people can interact with many, can have many interactions, participate in many events, for example, but then with a small set of different others, right? So does it make a difference for example, spreading processes if the network has a lot of large neighborhood size, or it's better if we have smaller neighborhood sizes but stronger ties, you know? So what's the balance between this popularity and the quality of the ties? Can these things actually be important for spreading process? I like, be it epidemics or opinions or innovation, whatever. So yeah, these are still open questions. So, and with that, I finish the talk. I hope I was not too much over time, and I'm happy to discuss and take questions.